Okay, we are ready to start our morning session in particle physics and phenomenology. And our first speaker today is Professor Mikhail Shaposhnikov from EPFL, and he will tell us about Einstein-Cartan gravity and its applications.
Thank you very much. Morning, everybody. Thanks, organizers, for inviting me here. So what I'm going to do today, I'm going to overview Einstein-Cartan gravity and some of its application in particle physics. And this is the list of references which you can look at for different details on this matter. And this is the work I was doing together with Andrei Shkerin, Sebastian Del, Yenar Timirazov, and George Karnanas over last few years. Okay, so I'll start with giving you kind of minimalistic approach to particle physics. And then I will come to Einstein-Cartan gravity and explain why I think that that's an interesting theory which can embrace particle physics, gravity, and cosmology. And then I will go through different applications of Einstein-Cartan gravity. They will be, some of them will be associated with the early universe, such as inflation and dark matter, and yet another one will be associated with, so to say, low energy physics, associated with the strong CP problem and axiom. Okay, so we want to construct some ultimate theory of nature, right? And this ultimate theory of nature should contain some components. So that should be at least the standard model, so gauge bosons of the standard model, gluons, W and Z bosons, photons, fermions, they're all discovered, the fermions of the standard model, Higgs boson, already discovered, gravity, spin to graviton, already discovered, gravitational waves. And since the standard model is not complete, it should contain few other particles which should be dealing with outstanding problems of the standard model, such as neutrino masses, dark matter, and baryon asymmetry of the universe. So what this minimal number of standard model particles of addition to the standard model could be, perhaps the simplest and most minimal possibility is to add to the standard model three right-handed neutrinos. So as you know, in the standard model, neutrinos are absolutely massless because they only come in left-handed components. These are, so to say, the holes in the standard model picture. Now, if these three particles are added, you can solve neutrino physics, all neutrino physics problem, get all neutrino physics right, neutrino oscillations, etc., etc. One of these particles can be dark matter candidate, and in addition to that, this theory gives a mechanism for producing baryon asymmetry of the universe, solving in this way all outstanding problems of the standard. Okay, so we have to unify all that in some common picture, and the question arises, what could be a action, Lagrangian, for this ultimate theory? So very symbolically, it may contain three pieces. So one of them is action or Lagrangian of the standard model. or of the new MSM. So the new MSM is the extension of the standard model by 3 right-handed neutrinos. Then there could be some gravity action and some mixing between the two. And the question is, okay, we know what action for the standard model is, or for new MSM, what is the action for gravity, and what is the action for this mixing between particle physics degrees of freedom and gravitational degrees of freedom. Okay, so let's start from gravity action. Well, what is gravity? If we go back to Einstein, we can say, well, gravity is something very much different from the standard model fields. It's not an ordinary force, but rather a property of space-time. And so to describe gravity, we should invent a theory which describes the change of geometry. And so this is geometrodynamics. And this is the way how gravity theory was developing. When I was giving lectures on general relativity, what you do, you start from principle of equivalence, and then you develop a geometrical viewpoint, introducing curvature, metric, etc., etc. So there are many arguments in favor of this point of view. There is, of course, strong experimental evidence and astronomical and human scales. Distances, the theory is mathematically beautiful. So if we go in this direction, perhaps construction of unifying all different interactions would be associated with geometrizing other forces of nature, such as electrodynamics or the standard model, grand unified theories, whatever. Okay, so that's one point of view. There could be another point of view. Just you can say, well, what is gravity? Gravity is absolutely nothing special. It's like electrodynamics. So what is specific for electrodynamics is that we have a massless particle, photon, which transmit electromagnetic interactions. And so gravity is just a theory which contains a massless graviton, spin 2, and geometry, etc., is nothing fundamental. It's just an effective field theory description of the theory which contains this massless gravity. Okay, so this point of view is also, well, it's attributed to Feynman. This theory this point of view is also very successful. It is based on success of quantum mechanics and quantum field theory in describing interaction of elementary particles. And if you say, okay, I would like to construct a quantum field theory which transmits electromagnetic interactions in a way that you have massless photon and in a way that it has massless graviton, then you are coming to electrodynamics and general relativity, as was shown by Weinberg quite a while ago. Okay, so what I'm going to do, I'm going to use this second type approach, and it leads me naturally to Einstein-Cartan gravity. So why so? And what is Einstein-Cartan gravity? What we have in particle physics, say the standard model. The standard model is based on the gauge principle. Okay, so you say, let me take a theory which has some global symmetry. It would be U1 for the case of electromagnetism, well, SU2 and SU3. So let's take all these symmetries global. Now, if we make a further step, we say that we replace these global symmetries by local symmetries, then we are coming to the standard model. Okay, we get photon, WZ boson, gluons, etc. But if you take the standard model, there is yet one more global symmetry here, which is not gauged. Okay, and this global symmetry is nothing but the Poincare symmetry is the Lorentz group. Okay, so the Q of T in Minkowski space is a theory which is local with respect to internal symmetries, but which is global with respect to the Lorentz group. So if we want to continue with the gauge principle, we better localize the Lorentz group. And there is a way to do so, which was suggested by this gentleman, Okitayama, Kibo, and Shiyama, who proposed how to localize the Lorentz group. And if you do so, then surprise, or perhaps not surprise, you are reproducing the general relativity. Okay? So you get a massless graviton. And this is not absolutely obvious, okay, because of a number of reasons. But let me tell you how this theory is constructed. Okay, so there are several gauge fields in Einstein-Cartan gravity. So one of them is actually very much familiar to everybody who studied general relativity, and this is just a tetrad 1,4. Okay, so roughly speaking, if you make a square of tetrad, then you are going to get a metric which tells you what are the distances in your theory. Okay, so tetrad itself, it has 16 fields, because there are 4 indices here, 4 indices there. So this index is, so to say, Minkowski index, and this index mu is an index associated with the curved space-time. And then once you have Lorentz group, so as you know very well, Lorentz group contains 6 generators, and as a result, you have 6 gauge fields, which are called spin connection 1 field. And so this is a guy with 1 curved space index and 2 Lorentz indices, A and B. And this indices A and B, they are anti-symmetrized, and they exactly correspond to the generator of the Lorentz group. Okay, so here you get 24 different components, 24 fields. So you have 16 plus 24, 40 different components. Okay, so you can say, well, how this can be a general relativity, which contains just 2 degrees of freedom, which are hidden in the metric, okay, to gravitons. We will see that in a second. But this is kind of construction very much familiar from the point of view of particle physics. So then what you do everything what you would do in gauge theories. You have these different elements, you know how they transform with respect to different transformations, all local transformations here. And so you should construct the quantities which can be called field strength. Okay, it's like an analog of F mu in electrodynamics or in SU2 or SU3 gauge theory. So you have to construct the objects which are changing, transforming in a homogeneous way once you make a gauge, local gauge transformation. And so there are two of these objects here. So one of them, you see it's just the field strength, which you would have in U1 gauge theory, SU2 gauge theory, which is constructed from the spin connection. And then you can construct yet another quantity, which is called torsion, and which is actually nothing but a combination of covariant derivatives of tetrad. Okay, so once these field strings are constructed, you proceed exactly in the same way as you do in gauge theories. So you start to find out what are the different invariants which do not transform when you make all these gauge transformations. And the lowest order invariants, they are presented here. So there is this field strength, tetrad, different epsilon symbols. So you make local Lorentz gauge transformation, it doesn't change. Then there is yet another combination which you can construct here from F. And then there are different components of torsion which can be also used for construction of the action of your theory. And these are written here. So I just put one of the indices of the torsion tensor down, and then you can use different contractions to organize the components which have a simpler transformation properties. So one of them is called the torsion vector. So this vector field contraction of tensor of T with respect to indices. If you do that with the epsilon tensor, you get another torsion vector. So it's axial torsion, axial because you have epsilon here. And then you can symmetrize in a certain way another three components, take away traces to get an irreducible representation. Okay, so these are the objects which you can use to construct the action of your theory. And if you do lowest order gravitational action, let's forget for a moment about other fields which are present in the standard model, then this is what you can write. You write one curvature, another curvature, and then different squares of the torsion vector, torsion tensor. So dimensionality is F is GV square, F tilde GV square, and torsion vector and torsion tensor are GV. Okay, and so to have something of dimensionality 4, you multiply it by some mass parameter. So if we are talking about pure gravity, then the action of the theory is here, okay? Because well, it has 40 components, has nothing to do with gravity, but then you start to analyze this theory, you can prove that this is nothing but Einstein gravity with two components. So why it happens so? It happens so because many fields which appear in this description are not dynamical. Okay, so how do you see that? You find the equation of motion for this field. So for instance, you make variation with respect to torsion vectors, and then you find that all these components are equal to 0, so torsion is not dynamical. Then the F and F tilde, they contain the field, the gauge field, okay, but in the first power, after you make variation, you also find out that this part is not dynamical, and so at the end of the day, what you're going to see that this theory is equivalent to simply Einstein gravity, with graviton containing 2 degrees of freedom. Okay, so this is one part which I'm going to use for construction of the theory. It is the same as Einstein theory if it's taken alone. That will not be the case when we add standard model. Okay, so for standard model action, so what we should do, we should also make this invariant with respect to all these symmetries, and exactly as we do in gauge theories, what we should do, we should make long derivatives accounting for the local Lorentz group. Okay, so for instance, for fermions, it would be an ordinary derivative and then the part associated with connection. Okay, and now we can also fix the mixing term. So what would be the mixing term? It will be different products of the parts coming from say Lorentz group and the parts coming from the standard model. And again, the terms of lowest dimensionality, they will have the form like square of the Higgs field times different curvatures, or square of the Higgs field times torsion, to make the part of the action which has dimensionality GeV to the 4th power. Okay, so then if we follow this principle, this fixes for us the total Lagrangian of the theory. Okay, mixing terms, gravity part, and standard model part. And what we can say, okay, let's imagine that this is ultimate theory of nature, and let's analyze its properties where this theory can do something helpful, something interesting for us. Okay, so the very first question is, what are degrees of freedom of this theory? And okay, since you have the action, you can analyze this question in a straightforward way. And then you find that the particle content of the theory is just the standard model, okay? And or new MSM with right-handed neutrinos plus graviton. Okay, so only 2 out of 40 degrees of freedom hidden in spin connection and tetrad are physical and propagating. So torsion is not dynamical as it used to be for pure gravity. Okay, but what you get is that because of torsion, because of all other degrees of freedom, the Lagrangian of this theory is different from that you would write for standard model plus Einstein gravity. Okay? You will get a non-polynomial kinetic term for the Higgs field, new fermion interaction between fermions of the new and the Higgs field, which were not a priori there if you just add the standard model Lagrangian and Einstein-Hilbert action. Okay, so let's take this theory and let's see what happens to it. So the very first question which I'm going to discuss is associated with inflation. Okay, so you know that if we have inflation, so inflation is a great theory which allows to explain why the universe is flat, homogeneous, and isotropic. Not only that, that it contains small fluctuations, it produces small fluctuations which can seed structure formation. Okay, so inflation, it implies that the universe was expanding exponentially at the very beginning in this de Sitter stage, precisely this de Sitter stage, which makes the universe flat, homogeneous, and isotropic, and then fluctuations of the scalar field around background give rise to density perturbations. So the question is, inflation, is it a signal of existence of new field, of a new particle? Is it some kind of new physics appearing there? The main requirements from cosmology for making inflation to work is nearly flat potential for large scale fields, if we talk about chaotic inflation, and also graceful exit from inflation. What graceful exit means is that when inflation is finished, there is some energy stored in the inflaton field, and then this energy stored in the inflaton field, it's go in some way into standard model particles. It should create a hot Big Bang, and so after that, the evolution of the universe is radiation, is dominated by radiation. Okay, and it happens that Higgs field itself, without addition of any new physics, can inflate the universe, and I'm going to show you how this happens in the Einstein-Cartan gravity I'm discussing here, but this happens even in the standard model plus Einstein gravity. It has non-minimal coupling to the Ricci scale. Okay, so the main point here is that if the Higgs field is coupled in a non-minimal way to the Ricci scalar, at large values of the Higgs field determines the Planck mass. It determines the constant of gravity. The constant of gravity increases when H field is increasing, and this means effectively that the potential for the Higgs field flattens up at large values of the Higgs field. Okay, and in this way, all the requirements which I formulated just a slide before are satisfied. So first, you have flat potential, and this flat potential leads to inflation, and then there are fluctuations. So this is really, you get really Mexican flat potential, contrary to that which you have in Phi-4 theory. Okay, so rotate this guy around the origin. So what happens at Higgs inflation is that at large values of the Higgs field slowly rolls down on the potential. Okay, and during this time, the universe gets flat, homogeneous, isotropic, and then later on, the slow roll finished, and the Higgs field start to move in this potential, and since it couples to the standard model field, it transfers its energy with ease to other fields of the standard model. That's solving the problem of graceful exit from inflation, and so you get the hot universe at the end of this stage. Okay, so now let's take our theory and see what happens in it and what kind of predictions can be made within this setup. Okay, so we have I throw away all fields in the standard model except the Higgs. So we just keep the Higgs field and our gravitational degrees of freedom, okay, taking away fermions, gauge bosons, etc. So what you see here is the standard model part of Lagrangian associated with the scalar field. This is potential, this is kinetic term. And then we have the gravity part, and then we have different mixing terms. So the gravity part, I'm now rewritten not in terms of the invariance which I introduced before, but some related invariants which you can construct in more familiar terms. Okay, so that would be m Planck squared times r. It's Einstein-Hilbert action associated with it. Then there is non-minimal coupling of the scalar field to r. And then there are extra terms which also have different names because they were invented by different people. So one of them is called Hall's term. So here you observe the connection of epsilon with r mu. If you take Einstein gravity, this type of term would be equal to 0 because of symmetries of the Riemann tensor. In Einstein-Cartan gravity, this structure doesn't have the symmetries because torsion is present. And so this is a non-trivial term. And then there is yet another non-minimal coupling, which is constructed from the torsion and which is multiplied by the Higgs field. Okay, so this actually contains several new parameters. There is this parameter which controls non-minimal coupling of this type, then this parameter which controls non-minimal coupling. This is also non-minimal coupling, and then there is yet another parameter which associated with the Hall's term. Okay, and then this theory is more general than Einstein gravity, and by the choice of different choice of these parameters, you can get Einstein gravity if you want. You can get Palatini gravity. So remember in Palatini gravity, how Palatini gravity is organized. It just said that in metric gravity, the only dynamical variable is the metric G mu, whereas in Palatini gravity, you say that there are two independent structures. One is Christoffel symbols, one structure is Christoffel symbols, another structure is G mu, and that gives you a somewhat different formulation. So anyway, by changing these parameters, you can navigate between different formulations of gravity. So now what you do, you this theory, and then you try to see what's happening in this theory in the real universe, in particular when the scalar field is large enough. Well, as I already said, because of all these non-minimal couplings which appear here, that potentially all these couplings rise to inflation, okay? Because when the scalar field is large enough, the Planck mass is proportional to the value of the Higgs field, and that leads to the flattening of the potential. Okay, so this is the same as previously in the Higgs inflation, but since there are many parameters appear in this theory, the inflation details can differ with different types of parameters. there is a technical trick which allows us to analyze this theory in a more simple way. And this technical trick is associated with making a certain Weil transformation which converts this theory into so-called Einstein frame. So here the theory is written in, so to say, Jordan frame, in which the Newton constant or the Planck mass are dependent on the scalar field. And what this Weil transformation does, it removes this dependence. So you get a theory in which the Planck scale or Newton constant are field independent. Okay, but after you do this transformation, you get a more complicated action in which kinetic term gets modified and the potential gets modified. So this is how this Weil transformation is acting. And so from here you see, for instance, that the potential for the Higgs field flattens at large values of the Higgs field, because it was proportional to the Higgs field to the fourth power. And this Weil transformation also contains h to the fourth. Okay, so you get flat potential, and then you get different modified kinetic terms. Okay, and then you can see what kind of inflation you can get in this theory. As I already said, certain parameters lead to equivalence of this theory to metric gravity. So you can analyze this theory and you can get a prediction for the scalar field and for the amplitude of gravitational waves. And this is all well in accordance with observations. You can make another choice of parameters, which, for instance, correspond to Palatini theory. You find the similar value for the scalar field, but much smaller tensor to scalar ratio. Okay, so this parameter is not fixed. It depends on different constants, which we don't know a priori. Yeah, by the way, in this case, the predictions of Higgs inflation are very close to that very first model of inflation proposed by Stravinsky. Now you can look at that even in a more general way. Say, well, there are all these parameters. Let's vary all these parameters. Let's see what happens. And what happens is kind of interesting. So this picture, it shows. So this is these are different values of different non-minimal couplings, and the color code along this line, it corresponds to the scalar tilt. And well, on this picture again, there are different non-minimal parameters, and color code corresponds to the different value of the tensor to scalar ratio. And well, basically the message from these pictures is that the two cases, Higgs inflation in the metric formulation and Higgs inflation in Palatini formulation, happen to be attractive points. Okay, so you change the parameters and you either get metric Higgs inflation or Palatini Higgs inflation, though you didn't choose parameters in the theory corresponding to these cases. Also, there are specific parameters which tell that the tensor to scalar ratio is not necessarily so small, it can be large. And if this is the case, then the theory may be experimentally tested with more ease than in the case of Higgs or Palatini inflation. So these are the conclusions for this part, and they are that in this theory, inflation is a generic phenomenon. A large part of parameter space reproduce predictions of either metric or Palatini Higgs inflation. And this means that the spectral index is mostly independent of the choice of couplings and is very close to this expression where n is the number of efoldings. The tensor to scalar ratio actually happens to be model dependent and can vary between the numbers of the order of 1 to very, very small numbers of the order of 10 to the minus 10. Okay, so I think with inflation, so I have, 15 minutes. And now I come into another question, which is now associated with another part of this theory related to the fermions. Okay, so how do you include fermions? You have to do that in a gauge invariant way. When I say gauge invariant, meaning it should be invariant with respect to the local gauge transformations. And this is the way how it should be done. There is a covariant derivative which contains a covariant derivative which you would write for the standard model, but now there is an extra piece corresponding to the spin connection field omega. Okay, and now you can realize immediately, since spin connection happens to be a non-dynamical field, so the spin connection is a vector field, so it's expressed through other parts of the standard model. And so in particular, spin connection contains a piece which is proportional to the fermionic current itself, and therefore, in this theory, you get 4 fermion interaction. Okay, and that was first found by Keeble. Okay, and then the strength of this 4 fermion interaction, it's associated with different constants which appear in formulation of this theory. And several types of this 4 fermion interaction. So one contains the axial current square, then there is vector current square, and then there is a mixing term. And what is the interesting point about this interaction is that it contains all fermions which appear in this theory. So if you skip to if you just say, okay, I just have a standard model, nothing else, then you get this fermion interaction, but then this fermion interaction doesn't change anything. Okay, it's suppressed by the Planck scale, well, maybe some parameters there, but this interaction doesn't bring anything new. However, if you have not a standard model, say extension of it, MSN with the right-handed fermions, or any other extension of the standard model which contains other type of fermions, then these fermions will be present here. And this means that these new fermions, they interact with the fermions of the standard model in this way. Okay, so for instance, if this is a dark matter fermion, then it contributes to this vector current or to the axial current, and this leads to a new process in which 2 fermions of the standard model collide and produce this new fermion. Okay, and this leads to a new mechanism for dark matter production. So if this new fermion is associated with the dark matter. Okay, so you can analyze this process. I am not going to do that with many details. So this is a rather standard analysis. You have fermion interaction, so you can compute the number of fermions produced and analyze what kind of mass the fermions can be produced, how it depends on the different coupling constant, etc., etc. So, for instance, if you say that, well, I don't have some non-minimal couplings in the fermion Lagrangian, and then you can see that you can get inflation and correct dark matter abundance for heavy fermions. Now, if you say that the non-minimal couplings and the fermionic Lagrangians are of the same order of magnitude as non-minimal couplings in the Higgs sector, then the fermions of the mass of the order of keV can be produced with this interaction, and that's an interesting possibility in the new MSM because of the following reason. There is an exclusion plot for right-handed neutrino being a dark matter. And this exclusion plot is shown here. So here you have a mass of keV sterile neutrino, and here you have a coupling of the sterile neutrino to ordinary fermions. And then there are different parts of these plots which were explored experimentally and which are excluded. So for instance, very light dark matter is not good because that would contradict to the phase density constraints associated with dwarf satellite galaxies. Then the part which is here, so if you are above this line, then you produce too many of these fermions simply due to their interaction with ordinary neutrinos. Then there are constraints coming from X-ray telescopes which forbid sufficiently large couplings. Okay, there is one suspicious point which would correspond to 7 keV neutrino, which was associated with suspicious finding of 3.5 keV line in different X-ray telescope. Well, this is a controversial question. Okay, and here there are also some limits from below, okay, which are associated with specific mechanism of production of this dark matter neutrinos through oscillations with ordinary neutrinos. Okay, and now if there is yet another mechanism of production of these particles, then this bottom part is simply removed. So they are produced by some other way. Okay, so now I'm coming to the very last part of my talk, which is associated with yet another idea, which, well, the previous theory, it contained many parameters, okay, all these non-minimal couplings on which different predictions depended. Gives some uneasy feeling, okay, we have a theory. It's much better than effective field theory. In effective field theory, you write whatever you want, you don't know what it is here, there is much less freedom. But let's see if we can limit the freedom even more and have even more symmetries in this theory. Okay, and here I'm coming to Weyl symmetry. Okay, so you know that Weyl there was this idea that all interactions should be geometrized, while introduced this symmetry, which basically tells that you can change the length of your ruler at every point of time. So this is a local symmetry. And Weil wanted to associate the gauge bosons related to the symmetry with the photon, so it didn't work because of different phenomenological constraints. But let's see if we add this symmetry to the picture, what are we going to gain? Anything? So by itself, that's a very interesting symmetry. Why? If you take Weil symmetry and limit your theory to the flat space-time, you discover that the resultant symmetry is conformally invariant. Okay, so conformal group, it's bigger than the correct group. It has 5 additional generators, special conformal transformations and dilatations. This is a symmetry of 3 Maxwell equations. Okay, so Lorentz group was discovered by studying Maxwell equations. Okay, conformal group was also discovered by studying 3 Maxwell equations. Also, what is interesting that if you take Lagrangian of the standard model, and put mass of the Higgs boson to 0 in this Lagrangian, you will find out that the total symmetry, global symmetry, there is not just Poincare, but it's a full conformal group. And that is interesting because mass of the Higgs boson is very small. So if you put mass of the Higgs boson to 0, then you increase the symmetry of your theory. And also the energy of the ground state in conformal field theory is equal to 0. Cosmological constant is also very small. So perhaps there is a connection. The Einstein-Cartan gravity amazingly provides a natural mechanism of implementing the Weil symmetry. So for Weil symmetry, you need some gauge field because you're making a gauge transformation. Like here, you are changing the metric. Okay, you are changing your length, and you can look at how different components of torsion, other fields, transform when you make the local Weil transformation, and then you will find out that the vector part of the torsion transforms like a gauge field. Okay, so you don't need to introduce anything extra. You just take your Einstein-Cartan theory, and in order to make it Weil invariant, just use long derivatives using the torsion as a gauge field of the Weil symmetry. Okay, there are also connections to Weil anomaly here. So this is there is no Weil anomaly here because the particle content is very much different. And now you say, okay, I now follow the same program. Okay? In addition to this formulation, I add Weil symmetry and take a theory and see what happens there. Okay, and then you're very much constrained. Okay, so in previous situation, the Planck mass was introduced by hands, but now it's not allowed because it breaks Weil invariance. You can only have dimensionless coupling constants. Okay, and so the only terms which are admitted are f squared and f tilde squared. Okay, if you add other terms which are consistent with symmetry, they could be also admitted, but they lead to a pathological theory which contains ghosts. And so if you don't want to have ghosts, I don't want to have ghosts, that's the only possibility we should have. And then you have different non-minimal couplings, which you should also organize in a way that it consistent with the Wild symmetry. Okay, so I'm running out of time, so I will squeeze a few things, just announce what is happening here. You have the action, and then you can proceed in the straightforward way. And what you find is that the result in theory now it's standard model plus gravity, but there is one extra degree of freedom, one new scalar particle. Okay, and this one new scalar particle and well, the properties of other essential pieces of the model are very interesting. It happens that the vacuum energy cosmological constant, you cannot write it from the very beginning, okay? But it appears dynamically, but it's proportional to the gauge coupling of the Lorentz group. The same happens with the Higgs field, and the same happens with the with this new particle. Okay, so you know phenomenologically, it would be great to get that from some fundamental principles that cosmological constant is small, say mass of the Higgs is small. This particle I want to identify with axion, that axion mass is small. They all happen to be proportional to the gauge coupling. Okay, so if you say that gravity or the gauge coupling of the Lorentz field is the smallest, it's really very, very small, then you get a unique bulk explanation, quote unquote, or at least you put on the same ground three outstanding problems, why cosmological constant is small, why the Higgs mass is small, and why the axion mass is small. They're all coming together. They're all associated with the smallness of the gauge coupling for the Lorentz group. Yeah, this coupling should be really small to make it work. Well, as I said, this new particle, it has all interactions which you would have for the axion, and therefore it can solve a strong CP problem. So you just, it's not coming from any Pichet-Quinn symmetry, it's just coming from requirement of Weyl invariance. And it's more economical from this point of view. And so I'm coming to my conclusions is that this theory, I think it's interesting. If you have, in the first part of my talk, I didn't discuss Weyl invariance, but this theory has the same number of degrees of freedom as the standard model. It leads to Higgs inflation with a pretty universal prediction for the scalar Thiel. It also leads to a new universal mechanism for fermion production in the early universe of matter. And if you add Weyl invariance, then you discover that there is one more degree of freedom, just one, nothing else. And this degree of freedom can play a role of the inflaton, sorry, of axion. And moreover, three problems: smallness of cosmological constant, of the Higgs mass, and of the axion, they're put on the same ground. Thank you very much for your attention.
Yes, thank you for your talk, and probably we have time only for one small question. If you have.
Okay, so small question. On slide 30, you were showing the right-handed neutrino constraints. You had different lines that were colored. What were they indicating? Were they some number of E-folds? On the slide 30, you had the canonical plot of the right-handed neutrino with respect to mixing angle.
Yes.
But what are the different theory curves?
These lines.
Yes.
Yeah, I didn't explain that. It's so these lines are associated with the following idea about production of this right-handed neutrinos. Okay, so let's just have standard model Lagrangian plus right-handed neutrinos. Okay, then there is a mixing between neutrinos active and still neutrinos, and let's compute the abundance of right-handed neutrinos which are related to this mix. Okay, so if you take the universe, which is symmetric with respect to lepton number, so no lepton asymmetry, then this is the line which you find. Okay, so you have to be on this line in order to get correct abundance of these neutrinos. Now, if the universe contains lepton asymmetry, then this line changes. And it moves down when you increase lepton asymmetry. And so these numbers, 25, 70, etc., these are characterization of this lepton asymmetry in some units. So for instance, here there is BBN limit. You cannot make lepton asymmetry too large. You will come in contradiction with the BBN. So this line would correspond to this. These are some intermediate numbers.
Okay. We have a very short break in 10 minutes, so I suggest to ask further questions in the short break. Okay, let's thank our speaker again.